So in week 2, we are going to focus on a book by Thomas Kuhn, one of the, possibly the most influential philosopher of science. And I think it's going to fit real well with week 1 because it's going to include some key scientific discoveries, and it's going to basically kind of take a big picture view, give you a different perspective on what you saw in week 1 in our survey of scientific discovery. So the structure of scientific revolutions is the title of this book. And one of the things I want to do with this is before you start reading it, or if you have already started, that's okay. I want to give you kind of an overview and kind of a model of how you might approach a piece of work like this that's pretty technical. Got some technical vocabulary and is talking about a lot of things that you might not have been exposed to before. How can you tackle something like this in terms of reading it and understanding it? Okay, so that's one of the things that I want to go over with you today. So the first thing I'm going to do is if I'm assigned to do a reading like this, I see the title, right? Okay, Structure of Scientific Revolution. So that gives me an idea of what it's talking about. It's pretty kind of esoteric and technical here, but scientific revolutions, at least I can grasp that part. We're talking about the big changes in science. Einstein's theory, Lavoisier's oxygen theory of combustion, things like that have Dalton's atomic theory, that have really changed science. The next thing I might want to do is, when you're reading a technical work, you don't want to approach it like a novel. Don't feel like you have to read it from front to back in order and you can't look ahead, all that sort of thing. Don't think about it like that. Instead, you want to start with kind of a big picture view and then kind of narrow down and focus. So the first thing I want to do probably is take a look at the contents. So just scan the contents. All right. This is the table of contents here. Sometimes the preface can be pretty helpful, by the way, when you're getting started reading something, and so don't just skip over that or neglect it. The introduction. Normally, the introduction is going to be a key thing to read. In this case, the introduction, I think, is probably, it's a little confusing, all right? But let's just scan down through here. The route to normal science. Okay, so I'm starting to pick up some vocabulary terms here. Normal science is one that we're going to want to talk about a little bit. Normal science as puzzle solving. Okay, well, puzzle solving is something I understand, and this seems to be equating the two things. Normal science as puzzle solving. In fact, as I'm looking at that, I'm thinking right now, hey, I can relate to that. Science is kind of like solving puzzles, and that's what scientists do. They look at problems as puzzles, and they try to figure out how the pieces all fit together. Next one, the priority of paradigms. Now we're getting into a little bit kind of an area that I'm not maybe comfortable with. I don't really know what a paradigm is. And the priority of paradigms, I don't even know what he means by priority, okay? But this paradigm term, it turns out, is going to be one of the keys to this whole book. Anomaly and the emergence of scientific discoveries. Okay, scientific discoveries, I got that. Emergence, okay, it's how this is what you saw in week 1. You saw the emergence of different discoveries through history. How about anomaly? So you get the idea here, I think. We're just going down through and kind of trying to get an overview from the table of contents. Now, I want to focus in for this week on 2 chapters here, what Kuhn calls sections. Section 6, Anomaly and the Emergence of Scientific Discoveries, and Section 10, Revolutions as Changes of Worldview. Now, I would encourage you to read more of that. These are going to be the 2 that you need to read to try to get through. Otherwise, I think you're going to miss out on the bulk of what we're trying to get at here. But I would encourage you to read as much of this as possible, especially the section from 6 through 10. So if you could read right from 6 through 10, that would be great. If you could read the whole book, even better. But definitely 6 and 10. So let's go to page 52 here to check out chapter 6. And I want to kind of model for you how to work through a difficult technical chapter. Okay, and this is, I think, on the PDF, it's around page 65 or so. There we go. Page 66, Anomaly and the Emergence of Scientific Discoveries. Now, I'm going to show you a technique here, and you don't have to use this particular technique, but it's called first, last. And when working through a technical piece of literature, you start by reading the first paragraph, then you read the first sentence in every paragraph, and then you read the last paragraph. And that is designed to give you an overview before you go into kind of a close reading where you read the whole thing carefully, take notes, highlight, mark it up, whatever you want to do. And let's just try that out and see how it works in this case. Anomaly and the Emergence of Scientific Discoveries. This is section 6. Notice we're jumping ahead here, so we skipped the first 5 chapters of the book. And I'm going to try to give you some background on this. But let's just see what we can do without having any background. So the first paragraph, normal science. The puzzle-solving activity we have just examined is a highly cumulative enterprise, eminently successful in its aim, the steady extension of the scope and precision of scientific knowledge. Wow, there's a lot to that, right? A couple of things I want to note, though, first of all, is this concept of normal science. All right, now, it's nice, though, here in that he actually kind of sums it up and defines it here for us. Normal science, the puzzle-solving activity we have just examined. Now, in Kuhn's view, normal science, the way science works most of the time, for example, right now in physics and chemistry and biology, for example, we're working in a period of what we call normal science. Now, normal science is contrasted with those periods of scientific revolution, when science is in crisis and then a whole new paradigm results. Normal science is a puzzle-solving activity. Basically, you have these solid theories in place, like Einstein's theories in physics and Darwin's theory in biology and the theories of genetics. And you're working with those theories to kind of build their applications, solve the remaining puzzles that they can solve, build up a database, a knowledge base from those theories. So you're basically taking the established theories and you're applying them again and again and again. You're trying to solve kind of outstanding problems around those theories, and you're doing applications of them and extending them. That's normal science. And he says that the aim of normal science is the steady extension of the scope and precision of scientific knowledge, which is what I just described. Now, what we're going to see is that Kuhn's whole theory here is that a lot of people think that that's all science is. That, in other words, most people look at science as the steady accumulation of knowledge that just continually builds on itself, and builds on itself. Kind of like, think about building a building, starting with a foundation, and you build a structure on top of that. Now, what Kuhn says is that is actually wrong, that there are periods when science functions like that. That's what he calls normal science. But there are these periods of revolution when science drastically changes, when the theories experience what's called a paradigm shift. And it's those paradigm shifts that Kuhn is famous for, that concept of a paradigm shift. Paradigm shift is kind of like a conversion experience when the scientist undergoes a change in worldview. The way they look at the world totally changes. Okay? So you can't look at it as an accumulation. It's like the whole thing changed. It's like now instead of building a house, you're building a spaceship, for example. The whole way you're looking at things changes. And that's really the essence of what he's saying now. It's not cumulative. Science is not cumulative. And you know what I mean by cumulative? It means accumulation and addition. But it's a total change in perspective that occurs periodically. Periodically, as we look through the history of science, we see drastic changes in perspective occurring at different times. Like when Darwin came up with his theory of evolution, or when Newton came up with his physical theories, or when Einstein kind of overturned Newton. So you see this development as we go through the history of science. So that's just a brief overview of where Kuhn is coming from, but it's a good to orient yourself. In fact, if you didn't have me to listen to and sum it up, it'd be a good idea before even starting this book to look it up on Wikipedia or look for a quick video on YouTube to just give you an orientation Where's this guy coming from? Okay, now he continues here, in all these respects it fits with great precision the most usual image of scientific work, which is just what I just said. Like, this is how people usually view science as working. Normal science does not aim at novelties of fact or theory, and when successful, it finds none. In other words, when science is successful, it's not going to find facts that contradict itself. Okay? It's not built to do that. New and unsuspected phenomena are, however, repeatedly uncovered by scientific research, and radical new theories have again and again been invented by scientists. Okay, so what happens, though, is science isn't always successful, and sometimes it does find novel facts. It finds things that don't fit. It finds what we call anomalies. And this is what brings about new theories, as we'll see as we read through these 2 chapters. History even suggests that the scientific enterprise has developed a uniquely powerful technique for producing surprises of this sort. If this characteristic of science is to be reconciled with what has already been said, then research under a paradigm must be a particularly effective way of inducing paradigm change. Remember, paradigm, it's not a theory, it's a whole way of looking at the world. Right now, we are under paradigm of looking at the world in a certain way. For example, evolution is a paradigm. Darwin's, or neo-Darwinism, this way of looking at the biological world. That is what fundamental novelties of fact and theory do. Produced inadvertently by a game played under one set of rules, their assimilation requires the elaboration of another set. So, for example, Darwin was playing the game of biology when he was out in the Galapagos Islands, and he found that the facts did not fit the current rules of the game, and so he changed the rules. He came up with a new paradigm. After they have become parts of science, the enterprise, at least of those specialists in whose particular field the novelties lie, is never quite the same again. Okay, we just finished the first paragraph. First, last. So next step, first sentence of each subsequent paragraph. We must now ask how changes of this sort can come about, considering first discoveries or novelties of fact, and then inventions or novelties of theory. Okay, so you can see how he's introducing some terms here. He's talking about fact, discoveries, theory. All right, so that's probably what this paragraph is about. It's kind of just a summary. Now let's look at the next paragraph. To see how closely factual and theoretical novelty are intertwined in scientific discovery, examine a particular famous example, the discovery of oxygen. Okay, so now this is cool. He's going to be talking about the story of the discovery of oxygen. And that's actually one of the things we're going to be focusing on in week 2, is the discovery of oxygen. There's a cool play up there that I'd encourage you to take a look at called Oxygen. And it really details this whole discovery process in a kind of a unique way. I'm not going to go on here, but I'm kind of tempted to read about these 3 different men who had legitimate claim to discovering oxygen. But let's scroll down to the next one, next paragraph. This pattern of discovery raises a question that can be asked about every novel phenomena that has ever entered the consciousness of scientists. So we're connecting this whole story of oxygen to a bigger question about how discovery works. How does scientific discovery work? Clearly, we need a new vocabulary and concepts for analyzing events like the discovery of oxygen. Okay, so we've apparently come up with the need for changing the way we look at things, at least according to Thomas Kuhn. Grant now that discovery involves an extended, though not necessarily long, process of conceptual assimilation. Okay, so he seems to be saying discovery is not just a single time event, like instantaneous event. It takes a period of time, and it's a kind of a gradual process. Two other and far briefer examples will reinforce much that has just been said and simultaneously carry us from an elucidation of the nature of discoveries toward an understanding of the circumstances under which they emerge in science. Okay, so we're going to look at 2 more examples. This is pretty cool. We're going to look at the discovery of X-rays and the Leyden Jar. Okay, so you'll see that as we scroll down here. Even so brief, an epitome reveals striking epitome. Now, one thing I'm going to encourage you to do as you read is look up words that you don't get. Now, typically, I might save this for the close reading step, which is next. But right now, I'm going to look this up. Epitome. Epitome definition. Because I'm not really clear how he's using that term here. A person or thing that is a perfect example of a particular quality or type. Okay. Even so brief an example, right, reveals striking resemblances to the discovery of oxygen before experimenting with red oxide of mercury. All right, that makes sense. Or right here, a summary of written work. Maybe that makes more sense, a summary. Even so brief, a summary, right? Before experimenting with red oxide of mercury, Lavoisier had performed experiments that did not produce the results anticipated under the phlogiston paradigm. Ah, phlogiston. What is that? Have you ever heard of phlogiston? See, before Lavoisier in the 1770s, phlogiston was the prominent theory of chemistry, and it was primarily a theory of combustion. Basically, what it said is that according to the phlogiston theory, phlogiston is kind of a sooty, greasy black substance that is released when things burn. So picture this, you're burning a stick, for example, and the smoke, phlogiston maybe, is being released. Okay, now it kind of makes sense because typically when things are burned, at least organic things like wood and paper and oil, their mass is apparently reduced. Of course, now we know that the reason that is because the carbon is combining with oxygen in the air and it's being released. But before Lavoisier, that's not how it was viewed. It was viewed as something being lost when something was burning. Okay. Now, another interesting aspect of this is that metals had their metallic characteristics like shininess and ductility and malleability and conductivity because of the presence of phlogiston. So what you would take is an element and add phlogiston and you would get a metal. Okay? Now when you burn that metal, what you'd be doing is releasing the phlogiston and you'd be left with what's called the elementary earth. So for example, if you burn iron, and it's true, you can burn iron, you'll get what we know as iron oxide or rust. To the phlogiston theorists, the phlogistic chemists, they would say that rust is an elemental earth. Okay? And that, you've heard of the four elements, earth and air and fire and water, right? So you'd get an elemental earth. And then if you recombined it with phlogiston, you'd make it into a metal again. By the way, you could do that by heating that thing, that earth, iron oxide. You could heat it with carbon, like charcoal. And what would happen is you get metallic iron out of it. And it's kind of an easy experiment to do. But that's basically how blast furnaces work. So this was the phlogiston theory. All right, and sorry, that was a bit of an aside, but I wanted to give you that background. Now, if you were reading this without me, again, when you hit that phlogiston, you might click over here, look up phlogiston, right? Nothing wrong with that. Don't just keep reading if you're just totally lost, right? Now I'm going to scroll down to the next paragraph. In a third area, however, the existence of significant parallels between the discoveries of oxygen and of X-rays is far less apparent. Okay, so he's talking about he's apparently listing some different ways in which these instances are similar, these examples are similar. X-rays, however, were greeted not only with surprise but with shock. Okay, so he's talking about now how people respond to these new findings. In short, consciously or not, the decision to employ a particular piece of apparatus and to use it in a particular way carries an assumption that only certain sorts of circumstances will arise. So this is why people might be surprised, because they're using a particular piece of apparatus like a cathode ray tube. Cathode ray tube, you're going to want to look that up, but we haven't seen that yet. You will when you read more closely here. And they get surprised by the outcome sometimes. That's the anomaly. Illustrations of this sort could be multiplied by reference, for example, to the belated identification of uranium fission. So we have a fourth example here, uranium fission. Moving on. Our final example of scientific discovery, that of the Leyden jar, belongs to a class that may be described as theory-induced. Okay, now you probably want to look up Leyden jar, and there's some really cool videos on YouTube. I'd encourage you to look up Leyden jar on YouTube to see what this is. Discovery of the Leyden jar displays all of these features as well as others we've observed before. To a greater or lesser extent, corresponding to the continuum from the shocking to the anticipated result, the characteristics common to all three examples above are characteristics of all discoveries from which new sorts of phenomena emerge. Okay, so he's summing it up. These examples, the stuff we've drawn from this, applies to everything in science, according to Kuhn. Even on the shortest exposures, many subjects identified most of the cards, and after a small increase, all the subjects identified them all. Okay, he's talking about cards here, so this is a little weird, and this is a really cool psychological experiment that he's describing here. Either as a metaphor or because it reflects the nature of the mind, that psychological experiment provides a wonderfully simple and cogent schema for the process of scientific discovery. Okay, this playing card experiment that he's describing is a model for what's happening in science. In the development of any science, the first received paradigm is usually felt to account quite successfully for most of the observations and experiments easily accessible to that science's practitioners. Okay, so he's talking now about the paradigm, the original worldview, is felt to account quite successfully, at least during the period of normal science. Ooh, and we are to the last paragraph, so let's go ahead and read this whole thing. So, what I just read, and then further development, therefore, ordinarily calls for the construction of elaborate equipment, the development of an esoteric vocabulary and skills, and a refinement of concepts that increasingly lessens their resemblance to their usual common sense prototypes. That professionalization, wow, this is some heavy stuff here, a lot of vocab. Basically what's happening is as the science gets more established, as that paradigm gets more established, people start to specialize, it gets very technical. And you get a lot of elaborate instrumentation that is built up around this paradigm that's designed to elaborate it, test it, apply it. That professionalization leads, on the one hand, to an immense restriction of the scientist's vision and to a considerable resistance to paradigm change. Now think about this. People are starting to specialize. They're spending whole careers studying this particular paradigm. That means they're going to be resistant to changing that. When you're 80 years old and you've been working for 60 years in a particular theory, publishing articles, and you're well known, you don't really want to say you were wrong all along. The science has become increasingly rigid. On the other hand, within those areas to which the paradigm directs the attention of the group, normal science leads to a detail of information and to a precision of the observation theory match that could be achieved in no other way. So it actually does a great job of matching facts to the theory until it produces anomalies. Furthermore, that detail and precision of match have a value that transcends their not always very high intrinsic interest. Without the special apparatus that is constructed mainly for anticipated functions, the results that lead ultimately to novelty could not occur. Okay. So what he seems to be saying here is that these apparatus themselves, the instruments that they're building, and this kind of detail that they're going into, kind of sets them up for creating anomalies or for detecting anomalies. And even when the apparatus exists, novelty ordinarily emerges only for the man who, knowing with precision what he should expect, is able to recognize that something has gone wrong. See, if they're making precise instruments, then it becomes more evident when something goes wrong, when the number is off. If your result is off from what it should be, and your measurement is sloppy, then you're just going to say, well, that's just because it was sloppy. But if your measurement is very precise and it's off, now you know something's not right. Anomaly appears only against the background provided by the paradigm. The more precise and far-reaching that paradigm is, the more sensitive an indicator it provides of anomaly, and hence of an occasion for paradigm change. In the normal mode of discovery, even resistance to change has a use that will be explored more fully in the next section. By ensuring that the paradigm will not be too easily surrendered, resistance guarantees that scientists will not be lightly distracted, and that the anomalies that lead to paradigm change will penetrate existing knowledge to the core. The very fact that a significant scientific novelty so often emerges simultaneously from several laboratories is an index both to the strongly traditional nature of normal science and to the completeness with which traditional pursuit prepares the way for its own change. So this last paragraph, in this case, gives us kind of a summary of what he's been saying, that these anomalies are generated by the paradigm itself, and that leads the way for its own change, for the paradigm's change. And that's what we're going to get into in Chapter 10. And again, I encourage you to read 7, 8, and 9 as well between these. I think it'll be better for you. But that's the first, last approach. So what that does is it gives us an overview. Now when we go back to the beginning, which is around page 65, 66, now what I'm going to do is what's called close reading. So I'm going to go into this now with a good picture of the landscape, and I'm going to actually run this race. So it's kind of like I've surveyed the course, and now I'm going to run this thing. I'm going to go through here, and I'm going to carefully read it. I'm going to look up words that I don't get. I'm going to take notes. I'm going to jot down questions that I have as I'm reading. Maybe make notes in the margin if you're going to print this out or if you got yourself a hard copy. And I'm going to read it for understanding. Now, whenever you are studying or reading, I would encourage you to take a kind of take this sort of approach. You can't stay focused like forever. Like, don't sit down and figure I'm just going to read solid for 2 hours. Okay, if you can read for say 20 minutes, really focus, and then take a short break, maybe like a 5-minute break or something. You'll find that probably a lot more helpful. Okay. But try to stay focused. So in other words, shut the phone off, turn the Facebook off, say to yourself, I am not going to look at this phone for the next 20 minutes. I'm going to focus on this. Then I'll take a short break, then I'll come back to it. Okay. Now, if you can push yourself to 40 or 50 minutes of focus, and then with a 10-minute break, that would be even better. But you might start with the 20 minutes or so. So take a look at that stuff, read 6 and 8, jot down some notes, and then you'll be ready to tackle this week's writing assignments and discussions.